So now I want to talk about the ETC and the APT quickly and give you a kind of framing of how this is going to work. So first, for the ETC, you're going to find that actually it's really similar to any ETC usage of SOS, and is pretty much identical. So you're going to have a bit of an easy time doing this, I think, if you're familiar with the ETC. And this is a little bit in contrast to NIRCam DHS, which had some subtleties last cycle that you might remember if you were involved in any proposals relating to like saturation and data rate, that really we're lucky enough not to have to worry about for SOS Multistripe. So if you're completely unfamiliar with the ETC, here's some links here to check it out and some tutorials. You'll definitely need it if you're interested in prepping a proposal. But otherwise, I'm just going to dive in, assuming you have some kind of low-level understanding. Okay, so first off, you want to specify sources and scenes. You're probably familiar with this. In this case, I've got two scenes and two sources I'm imagining. First one is this target HD219134. If you don't know this phone number, this is actually the brightest transit host we know of. It's got a JMAG of 3.86. And we have this other example just for this the sake of comparison, which is an arbitrary target at J equals 8.4, which is the substrip 256 bright limit. So we specified these and put them into separate scenes, and then we can start to make some calculations. So we pick NIRISS SOS, and then we want to use a standard setup for the instrument. We're just using the regular disperser and the clear filter. And now the subtlety really comes in the detector setup. And here we just want to pick our multi-stripe subarrays. So here I'm going to pick sub 17 stripe. If you remember, this is the smallest stripe size. So we're reading out the detector as quickly as possible, which lets us get to this brightest detection limit. So the first example is back to HD219134. So this is the brightest transit host, as I mentioned. So here we're at 3.86 Vega mag, and we're at maximum fraction of saturation of 0.72. So two groups before saturation. And I'll note this is like ETC saturation as well, which is technically not the same as detector full well. I know people like to go over the ETC saturation, so just keep that in mind, is that you do have some wiggle room if you wanted to do detector full well instead of the ETC nominal saturation. And you can find on JDocs information on what these saturation limits are relative to the actual detector full well. And you can see nicely that we're getting a NIRISS SOS observation with no saturation and a really nice high quality signal to noise of around above 300-ish to 200-ish across the entire wavelength range. Example 2 is substrip 256 versus sub 6080 stripe. So in here, this is where I have two cases. We have one where we're doing that J equals 8.4 target. That's calculation 2, and one where we have the substrip 680 stripe. This is calculation 3. So we can see we're just changing subarray, but we have the same target. And here's where you can start to see the signal to noise drop off more effectively, right? We have the same magnitude target here. The only thing we're changing is the subarray size or the subarray readout. And because we're reading out only a third of the detector at any given time, the total integration time is reduced by roughly a factor of 3, and our signal to noise drops accordingly. So this might be a situation, for example, where you would say, if you're experiencing some saturation, you would say, you know what, having double the signal to noise is worth it to me over having saturation in maybe 10 of my pixel columns. But again, it's totally up to your science case. Okay, so one big thing I'm sure people are wondering about is Pandexo. So if you're not familiar, this is like a dedicated ETC tool just for transiting exoplanet science. And that gives you the wavelength-dependent transit depth signal to noise, which is more useful, right, for your proposal motivations, prepping preliminary model fits and retrievals. SOS Multistripe, as well as NIRCam DHS and ETC 5.0 in general, are unlikely to be supported for the cycle 5 deadline. So we're making no commitment that will be in place, unfortunately. But for SOS Multistripe, don't fear, because there is a way that you can predict the signal to noise anyway. And that's what I'm going to go through now. So this requires some understanding of how to estimate transit depth uncertainty. And in this case, what we can do is we can imagine transit as a simple kind of box cutoff in the light curve, in which case numerically we can estimate the transit depth uncertainty as 1 over the signal to noise for a given integration. So that tells us how many points in the light curve we have, multiplied by this factor, which includes the number of in and out of transit measurements. And you can imagine that like just on a statistical basis, like how many points do I have on the baseline? How many points do I have on the transit within transit? And what does that tell me about my ability to measure the difference between the two, the transit depth? And you can kind of visualize this equation a little bit, right? If your signal to noise goes up, your transit depth uncertainty goes down. That makes sense. If you have more measurements in or out of transit, then your transit depth uncertainty, then this fraction is also going to go down, and your transit depth uncertainty is going to go down as well. Okay, so how do we get these pieces of this equation and estimate this thing on the left? Well, first, for the signal to noise, we can grab this straight from the ETC. So I just showed you how to generate a calculation. Once you've finalized your subarray choice and the number of groups you want to do, you can download the ETC products. So this is just a tab in the bottom right. You can click it here and you get this tar file. And if we open that up, you're looking for one file in particular, and that's this line plot underscore SN, so signal to noise, which describes the signal to noise as a function of wavelength. There's like a quick 4-liner for how to read it in. It's very simple. It's just a FITS file. And then you can see this this curve, which I was kind of showing a little bit in the earlier slides, that just tells us the signal to noise versus the wavelength. So that's perfect. That's our integration level signal to noise. Now, the next thing we need to figure out is N in and N out. So really, this is a fundamental level going to be defined by the time in transit and the time out of transit and the time for an integration. So in transit, it's quite easy to figure out, right? Because you can't change it. You know, your target is going to tell you what the transit duration is, and that's going to tell you the time in transit. The time out of transit, you're going to have to define for yourself. Typically, it's twice the transit duration plus an hour, but some people might want a longer baseline. Some people might want a shorter one to squeeze it into a certain proposal category. Really, it's up to you, but that will dictate that the T out is whatever is not in T in, but is in your total exposure time. And then the time for an integration, which is the trickier thing to figure out, and I'll show you how to do that. So this is the important thing, and I want to emphasize T integration for multi-stripe subarrays in this framework is not the value in ETC. Because in ETC, this tells you the time for a single stripe. And you can imagine like we're doing stripe by stripe along the detector. That might take me 21 seconds to do, but the time to just do one of those stripes is 0.18 seconds. So for any given point along there, I'm only exposing for 0.18 seconds. So to figure out T integration, you need to account for that and the number of points you're going to get. And that's relatively straightforward. You just need to multiply that time in the ETC by the number of stripes in the multi-stripe. So in this case, it would be 3, right? And that would give you your total integration. And you always have the number of stripes available to you because you have the stripe size in the subarray name. And then we always have, for all of the multi-stripe subarrays, a fixed number of pixel columns in the image we're constructing, right? And that's 2040. So you can divide that by the stripe size, times it by that time in the ETC, and you're good to go. So putting that all together, you get this like equation. Maybe it looks a bit horrible to some people. It's pretty simple, I promise. You just need to get these like 4 quantities out. So again, reminder, SNRI, we're grabbing that for the ETC calculation. T in and T out, that's defined by you for your transit observation. 2040 is just this fixed number. That's the size of our multi-stripe image. You can grab the time from the ETC from the exposure time in the ETC. And then the stripe size comes from your multi-stripe subarray name. So we can put this all together here for that case study I put in the ETC. So in this case, we're doing HD219134B. So transit duration is about an hour. Let's say we do our observation duration of roughly 3 hours. So we have 3,000-ish seconds in transit, 7,000 seconds out of transit. We know the subarray choice is substrip 17 because this is incredibly bright, and that's the only way we can observe without saturation. And that ETC time is 0.18 seconds. So we can do this quick math together and spit out this curve here. Now, I do have a quick Jupyter notebook that goes through this. Thanks very much to Manazir Alam as well, who shared me like a core, which I built it off from NIRCam DHS. And we're hoping to be able to share that with everyone, along with the PDF of the slides at the end of the JWebbinar. So you'll have that as well. You can just kind of plug in the values and get a curve like this for you to figure out whether you're getting the transit depth precision you need. Okay, so then the last thing I just want to cover quickly is the APT. So these are now available in APT 2025.5.2. This is released on August 22nd, so that's only last week. So if you haven't updated your APT in a while, you should do it to make sure you have full access to all of the capabilities and everything's working right. And again, similar to the ETC for Multistripe, this is pretty straightforward. You know, when we're not doing anything fancy, there is a little bit of new functionality which I'll go over. And again, like I don't have time to cover the general capabilities of APT, but if you do need help, here's a link to download it and another link for the tutorials. So first off, we'll start a new observation here with SOSS, as you would regularly. We're going to specify our target acquisition. You would specify a target normally as well. I've been too lazy and haven't put it in, but you will understand how it works. And then we pick our desired subarray. So in this case, you know, you can see just alongside the regular subarrays, we now have the sub 17, 60, 204, and 680 stripe. We can pick one of those and we can specify our exposure parameters. So in this case, I've just arbitrarily decided, okay, I want 3 groups in every ramp and I want 547 integrations to give me roughly a 5-hour exposure time. And you'll see, even though I've done this pretty standardly, I have an error, this red cross to the left. Now, this is important to pick up on because it's one kind of quirk about multistripe. Now, you may have seen these before in terms of like warnings, right? So this exposure duration goes over 10,000 seconds. Most transit people will understand that and know it's not a huge issue and can be justified in your proposal. It's these other 2 errors that we're really concerned about. So 1, integrations per exposure 547 is too large. The legal range is 1 to 546. And then the second one, the number of frames over roughly 200,000 is greater than this maximum allowed value. So what we're bumping into here is a telescope limitation in that we can only include so many integrations, so many frames, sorry, per exposure. Now, for a standard substrip 256, that's pretty normal. You wouldn't ever hit this limit, but some people who have performed phase curve observations may have seen this for other modes. And really what's happening here is because we're splitting up the subarray a lot, now every stripe counts as its own integration, its own frame, and we hit this number way, way quicker than you would normally. So there's this new functionality for SOSS, which already existed for NIRCam and NISPEC, I think, is exposures per dither parameter. And the way that works is basically you input your number, and that's how many times your exposure is going to be repeated. So we're just sidestepping this like intrinsic barrier in total number of integrations to hit that. So in this case, I've just halved my number of integrations and multiplied the number of exposures per dither by 2. If you want to fine tune that, you'd be more than welcome to. So one thing you will see is I did this for sub 17 stripe. That's a 5-hour observation before this happens. And really, this is the worst case scenario. As you get higher in the stripe sizes, you have less integrations in general, less frames. So it's easier, it's less difficult to kind of break this limit. So for, I forget for the sub 60, you know, you probably be way above 10 or 15 hours before this happens. But if you're observing something really bright with a long transit duration or a long baseline that you want to get, you just want to keep this in mind. And then quickly, I'll add just a callback to the earlier slides. If you want to include an F277W exposure or a short first exposure, which we generally recommend you do, by the way, the instrument scientists here, we're quite supportive of you doing this. It helps with calibration. It will also help you in flagging out where your contaminants are so that you don't get tricked, see some kind of narrow feature that you think might be from the atmosphere of the planet or similar. So here, yeah, we just recommend you mimic the number of groups from the observation and just set the integrations to 10. So yeah, very similar to a standard SOSS observation. the future plans for the SOS calibration. At the moment, we're yet to test on sky, right? The actual observation precisions might differ a little bit from the ETC, so just keep that in mind. The calibration effort is still being designed, but right now we're going to cover some generic things like dark observations for each subarray, wavelength and photometric calibration. Hopefully, ideally, really, the wavelength and photometric calibration should be identical to the current substrip 256. And the other thing we're going to be trying, hopefully, is a time series observation of a high signal to noise featureless exoplanet transit to make sure everything's working correctly and the pipeline operates correctly. Okay, so quick summary. We have these new multi-stripe subarrays. They're available for cycle 5. They offer significantly improved bright limits up to J equals 3.5, but give you the full wavelength coverage of SOS. That expands the SOS access to every known transit host. So please go crazy, observe whatever you want to observe. The data are going to be recorded in a slightly non-standard way, right? We're chunking things up and then joining it back together. So you might want to keep that in mind when it comes down to the data reduction stages. SNR losses, and I want to keep emphasizing this, but they really can be significant at these bright limits boundaries between different subarrays. So please be cautious about that. It would be great for you to maximize your observations and get the best science out you can. And then finally, the full ETC and APT support is available, but not Pandexo. And you can refer to those earlier slides. I actually think these numbers might be wrong, so I'll quickly update the slides when I share the slide deck around. But you can check that out to estimate transit depth uncertainties for your proposals. Okay, some quick links. Obviously, if you have more questions, you can ask me right now. But the other port of call, if you're watching this online or if something crops up later, is please reach out to the help desk. A ticket will come straight to me or the SOS team. We'll be happy to help you. And there's some other relevant JDocs links that kind of describe a lot of the stuff I've gone through today that you can read at your own time to figure things out.